Mic is not working. Can you please come? Mic is not working. Just come forward. Quickly explain some of the questions that you have posted on Piazza. From assignment 2, there was a question. In question number 1, 2.2 subpart, it is written that the matrix is covariance matrix is spherical. Is this for initialization only or at every step? It is only for the initialization. See, you can assume your covariance to be spherical in your initialization part, and as you train or as you start fitting your GMM, right, that depends on your data points, right? That depends on your training data points, whether your covariance will become spherical or not, that depends on your training data points. Okay, so the answer is it's only for your initialization. That assumption is only for your initialization. So one more question was actually one student was asking me to explain this formula. These are the number of parameters or trainable parameters in your GMM model, assuming your data to be d-dimensional. Each data point is d-dimensional and you are fitting k number of Gaussians. So in such cases, you will have k into d for your mu vectors, because your each mu will be a vector of d dimension, right? And then you have such mu's like k number of mu vectors you will be having. So it is k into d, and then the covariance matrix is anyway symmetric, so you just have to learn diagonal and one side of your off diagonal elements, right? So that turns out to be your d into d minus 1 by 2, and you have this many number of parameters k times, because you have k Gaussians. That is one. And then sorry, this will be capital K, right? Because you have pi, each pi k, a single parameter you will be having for each Gaussian, then that becomes k number of pi's, right? So you have k plus k. So this is the formula that we have. And one more question was, see, I had told you that whenever you are doing matrix differentiation, right, when you are writing the, like when you apply your chain rule and write the next integration, next derivation as the product, suppose you have x transpose ax, right? So this, if you are differentiating with respect to a, or suppose something like a inverse you have, if you are differentiating this with respect to a, as per your formula you will be getting x into x transpose, right, into, you have to take the derivative inside your a. See, ideally you will be getting a inverse by a, right? Differentiation you have to apply to a inverse. So in general we will be adding it here, right? If we apply, like in general simple functions, whenever we apply differentiation, we will add our next term like this. But in your matrix differentiation, you have to add it at the front. So that's what I have corrected, and this one we have followed the same in our linear regression case also, if you recall. Okay, that was the question. The question was, did we follow the same thing in the linear regression also? Yes, we have followed the same thing. So one more small thing that is remaining in your GMM, I'll just cover that and we'll start decision trees. Okay. So in your GMM, like I have told you, we'll be using an iterative algorithm to fit your GMM, that is your expectation maximization, right? So in your expectation maximization, you have your E step and you have your M step. In your E step, you will be computing your responsibility terms with your initialized or your previous, what can I say, this is t minus 1. So based on the previous mu's and sigmas and pi k's, you will be computing the responsibility terms, and using this responsibility term, again you will be updating your parameters, right? This will be again computed from using your responsibility term from your E step, right? This is what we have done, and this you have to run it iteratively till the convergence, and we have defined the convergence criteria also, right? Stopping criterion also we have defined. So in your k-means, what do you do generally in k-means? Like given your data, you will again assume your k, that is your, like how many number of clusters you will be having, the k you will assume, and you will initialize your centroids. You agree with me? The centroids will be initialized based on your maybe centroid 1, centroid 2 till your centroid k, right? These many centroids will be initialized. Do you agree with me? You know the pseudo code for your k-means, right? We will assume the centroids, and then in the next step what we will do, there is something called assignment step. In the assignment step, maybe I'll just open here. So in your k-means clustering, given some data points, assume that these are the data points given to you. So in this 3 clusters are possible, so you assume your k to be 3, and then we randomly initialize the centroids, and after initialization, what the next step is to do your assignment, right? Assignment meaning you will actually measure the distance between each data point to the centroids, right? Based on the minimum distance, you will actually label the data point. Each data point, basically this data point, if you see the distance between this centroid and the distance between this centroid and this distance between this centroid, we will calculate. Based on the minimum, we will give the label to this data point, right? That's what we do in our k-means. Okay, so like this we have to repeat the same procedure for every data point, and we have to label the data points based on the current centroids, right? That comes under your assignment step. And in your refitting step, like based on the assignments that you have, again you will update your centroids, right? So the centroids will be updated based on these data points, okay? Centroids will be updated. So this is an example. Assume that these kind of data points are given to you, and you have initialized your centroids to be here, and in the next step, based on the minimum distance, you will label your data points, and then again you will recompute your centroids, and this will be repeated, right, in your k-means clustering. Assignment step and refitting step. Can you relate to our GMM now? In GMM also we are kind of doing assignment and refitting. In your assignment, this assignment step is equivalent to your E step, where you are computing your responsibility terms. Is this fine? Were you able to relate? So this is the k-means, you are just doing hard assignment, right? Hard assignment meaning at the end when you do your clustering, you have got this, meaning that you are saying all of these red color data points belongs to cluster number 1 and these belongs to cluster number 2, but you didn't give any probability estimate, right? But in your GMM you will be getting your probability estimate. You will be getting, like suppose if you fit a bimodal GMM to this kind of data, okay, where k is equals to 2, and if you fit a GMM with k is equals to 2, At the end, to every data point, you will be getting a pi, right? Pi 1 and pi 2, sorry, pi 1 and pi 2 for each data point you will get. So that will tell you what is the probability that that particular data point belongs to cluster number 1 and cluster number 2. So that is called your soft assignment, which we have seen in the first class. Okay. So that's it. Actually, in your GMM, generally this is how we will fit our GMM. And in your k-means clustering, you have assignment step and refitting step. In your GMM, you have E step and M step. E step is kind of giving you the responsibility terms. The responsibility terms are equivalent to your assigning each data point to a cluster, because responsibility terms are giving you the probability estimates, right? Confused? Is it okay? So here in this case, if you see, if we are fitting a Gaussian mixture model for this kind of data, again we will do the same thing. We will initialize our pi case, sigma case and mu case, right? So in this case, I am initializing my maybe mu1 here and mu2 here, and if you see, I am actually taking a circular Gaussian. Can you tell me what am I assuming here? Am I assuming any correlation or am I not assuming correlation? Here I am assuming my sigma to be, or my Gaussian to be circular, and this case is equivalent to what? See, your Gaussian will be elliptical if there is some correlation between your x1 and x2, right? If there is no correlation, you will get a circle. So with my assumption here is I'm assuming they are independent or they are not correlated, right? So I am assuming my mu1 sigma 1 here and mu2 sigma 2 here, and then I'll repeat my steps. Okay, E step and M step. So after M step, then your mu's are actually, your mu's may be shifted to here and your mu shifted to here, and your sigma also changed. Even though you assumed it to be circular, you got it as elliptical. This is happening because you included your training data points, right? In the first step, when you are randomly initializing, you may assume it to be circular because you have no information. But once you start fitting based on the data, the shape of the Gaussian is changing, right? This answers the question also, the last question also. Only in the initialization you are assuming something, but when you are actually fitting your data based on the data points, the shape of your Gaussian and the mean will change. Okay, is this fine? Now can you relate your GMM with your k-means? K-means is kind of doing hard assignment, but your GMM is a kind of clustering, but it is probabilistic clustering and it is giving you the probability estimates also. So now let's come back to decision trees. So till now, if you observe, all the algorithms that we have learned are kind of parametric models, right? So we start with our linear regression, logistic regression and Bayes classifier. What else we have seen? These, no? And GMM estimation. All of these are, if you assume, either in, see, we have done classification using two approaches. One is the discriminative learning. Discriminative learning is nothing but where and generative based approaches. Okay. So in your discriminative approaches, basically your least squares and logistic regression will come under your discriminative approaches, where given some data points, suppose if I have some two classes of data, labeled data basically, okay, the labeled data is given to me and I actually try to fit this decision boundary only, right? In my logistic regression, I concentrated on learning only the decision boundary, right? Even in my least squares also, we try to find only the decision boundary, right? We concentrated on finding the decision boundary which will discriminate my data points. That's what we have done in logistic regression and least square. But when it comes to Bayes classifier, I have actually, if this is class 1 and class 2, I went and fitted my conditional PDF, right? This P of x given C1 and P of x given C2, these two conditional PDFs are learned in your Bayes classifier, and you didn't learn this. In your Bayes classifier, you didn't learn the decision boundary, right? You learned your conditional PDFs, and based on the conditional PDFs, you actually you can do your testing, like you can actually do your classification using the distributions that you have fitted, right? These distributions are parameterized again. These distributions are parameterized to be your mu1 and sigma 2, mu2 and sigma 2, and these parameters are learned with your data, and using these PDFs you are doing the classification, right? And you commented on the decision boundary also in this case, right? There are like the decision boundary can be linear if there is a condition that your mu1 and mu2 are same, and like sigma 1 and sigma 2 are same, something like that. You had derived the condition, you have actually commented on the decision boundary of your Bayes classifier, right? It can be linear or it can be non-linear also, based on your mu1 and sigma 1 and sigma 1 and sigma 2, and if they are equal you will have linear, and if they are not equal you will have non-linear. But you didn't actually go and learn the boundary, you learned only the PDFs, and using those you are actually doing the classification, right? And in our GMM, it's not at all about classification. We are working with unlabeled data, just the unlabeled data. Some data points are given to me. Okay, then I started fitting my density function. As this data, if you see, if this is my single data point, okay, single data set with 2 dimensions. So if this kind of data is given to me, I actually fitted my Gaussian mixture model using 3 Gaussians, k is equals to 3 and d is equals to 2, right? Using these k is equals to 3 and d is equals to 2 setting, I am actually modeling my distribution function, that is multimodal distribution, and that is your Gaussian mixture model. This we have done in our GMM, right, which is completely unsupervised setting and unlabeled data. Now, when it comes to decision trees, what we will do is, we will actually not learn any parameterized model, but to do the same classification, we will try to come up with a rule-based algorithm. Okay, we will come up with some rules, so that using those rules, we will try to classify the data. But it is not a parameterized model. Okay, did you get my point? We'll see what. Have you seen decision trees already? No, right? So it's all about coming up with the rules to do your classification. So it's and you will come up with some hierarchy of the rules. Okay. So to do your classification, suppose if you have, if you want to just grade students based on just pass fail, you will have a rule, and that rule you will apply, and based on that you will just divide the entire classroom into pass and fail category, right? If you have one level of you need only one feature here, just the number of marks you need to decide whether it is pass or fail. So if you are depending on one feature, then you can actually come up with a rule which is like just a single rule is enough. But if you have more number of features in your data points, then you have to come up with the hierarchy of the rules to do your classification. Okay, suppose in this case, if you see, if you want to classify your animals into mammals and non-mammals, so basically they are making use of this feature first. The feature is your body temperature based on whether it is warm or cold, and once the body temperature is used to do your classification, if it is cold, they are classifying it completely to be non-mammal, and within this set where your body temperature is warm, you have to further classify based on some more rule, because there is some uncertainty. Maybe the animals with warm nature can be mammal or cannot be mammal. If that uncertainty is there, then you have to come up with one more rule, right? So this is one more rule, and they are based on that one more rule they are doing classification. So in decision trees, our aim is to come up with these rules at each node. Okay, and you have to make use of your training data and come up with these rules. Okay, so in your, like, if you actually come up with this tree using your training data, then when the test sample comes, then you have to pass it through this decision tree or pass it through these rules basically, and then you can actually predict the test label. Okay, so we'll see that in detail. Yeah, so this is like at the end, these are called leaf nodes and this is called your root node. So maybe let's see this example. So this example, like blue color data points are one class and your red color data points are other class. Okay, so if I ask you to draw a decision boundary for this kind of data set, how will you draw? Maybe something like this. Something like this works, right? Because a simple linear boundary will not work here, right? This data is a bit of complex. It's non-linearly distributed. A simple line will not classify these data points. Do you agree with me? A simple line is not sufficient. But if I draw something like this, these boundaries, maybe this one and this one, will actually classify your data points correctly, right? So this this kind of decision boundary, how to come up with this using your decision tree is a question now. So this is the expected boundary for this kind of distribution. So now, this one, how to learn using the rule based algorithm. This kind of decision boundary, how to learn this kind of decision boundary using the rule based algorithm. The rule based algorithm that I have told you is the decision tree, right? So the rule, how to come up with the rules. Okay, so now if you see, the first rule is I am keeping a condition on my x1. Okay, so if x1 is less than 3, this is one set, and x1 is greater than 3 is one set. So I am actually coming up with my first rule, just given a data point x, so that x is greater than 3. If it is yes, it will go to this set, or if it is no, it comes to this set. Okay, maybe greater than or equals to, you can just keep. Okay, so then you are doing the first, you are applying the first rule on your data points, and in this you are considering x1 feature. Your x is a combination of x1 and x2. It is having two features, but you are considering only the first feature, and you are dividing your entire data region into two sets. Okay, so one is your S1 and S2. Okay, so after this, you have applied only the rule on x1, right? So then you have come up with this S1 set and S2 set. Now if you want to do the classification further, like within S1, if you want to classify your blue color and your red color, your class 1 and class 2, you have to come up with a rule on x2, right? Because x1 you have used and you have what divided your entire data region into two sets, S1 and S2. Now on S1, can you tell me any rule for my X2 to do the perfect classification? In this set, S1 set, where X1 is less than 3, can you tell me a rule on X2 so that I can do my classification perfectly? X2, it is not Y, it is X2. X2 greater than equals to 1, right? So this rule you can apply on this set, and then if it is S and if it is no. If it is S, it belongs to which class? Blue, right? Then if it is no, right? Then can you tell me a rule on rule for my S2? I have to go to my S2 now. In my S2 also there is uncertainty because the data points are mixed. So I have to come up with one more rule, right? So what is the rule in my S2? Somewhere here. So X2 greater than or equals to 3. Do you agree with that? X2 greater than or equals to 3. Then if it is greater than 3, red, right? Is this fine? So now in this case, if you see a simple data points or simple data set which is non-linearly distributed, and the data set is having 2 dimensions. So you have come up with like basically 2-level tree. No, you have a root node first. The main feature became your x1 here. X1 became the first feature in your root node to do your classification. One level of classification is done using a rule which we have set on our x1 feature or feature number 1, and later like you have divided your data points into S1 and S2 based on your feature number 1. So within S1, if you see, within S1 data set, within S1 set, you have again some mix of data points. It is not completely pure in this in decision tree terminology, right? If you have data points which are like which are having same label, then you will say that that set is pure. Okay, so after applying your first rule, you are getting S1 and S2, right? The S1 is not pure and S2 is also not pure. So you have to come up with one more rule to make it pure. Okay, so maybe I will just try to write this down. I'll give. So this one, right? This one I am making it S3, S4, S5 and S6. Okay, so this is what? This one is your S4. S4. Do you agree with that? This is your S4. And this is what? S3, right? And this is X2 is greater than 5, this is S5 and this is S6. Is this okay? The branches I am actually, okay, I will redraw it again. I'll redraw it again. Okay, so this one, if you apply your rule of x2 greater than or equals to 1, and here one more rule is x2 greater than or equals to 3. Okay, so can you apply these rules and tell me the sets here? To apply this rule, you have to go within S1, right? So this branch is actually giving you only S1 set. So you have to go within S1 and do the classification. So then if you apply this rule on X2, then X2 is greater than 1 is S3, X2 is less than 1 is your S4. Do you agree with that? Okay. So here this is what X2 is greater than 3 is S5 and this is your S6. This is fine. Okay, so like this I have applied my first rule on my X1 feature 1 and I have come up with 2 more rules. In this sub branch one rule on my X2, the rule is different, and in this sub branch the rule is different, but the rule is applied on my X2. Okay, so if you see this S3, S4 and S5, S6, if you see the common thing between all of these sets is they are pure. It means that in S3 if you see all the data points are having blue color only in S3, and in S4 all are having red color, and S5 is red and S6 is blue, right? But in my S1 if you observe, S1 is having some uncertainty. It is having the mix of blue and red. It means that S1 is not pure. Okay, so your decision tree you need to construct till the point where all of the sets will become pure. If the set is unpure, it means that there is still there is still scope to add some rules and do some classification if the set is unpure. Okay, so if you see when I apply my first rule, I got S1 and S2, and S1 and S2 both are unpure. So then I have came up with 2 more rules. Within my S1 I applied one rule and came up with this kind of classification, and this kind of classification in my S2. Okay, so now the question is, this is how we have actually classified, and this is possible with my 2-level decision tree, right? And here my rule is what? X1 greater than or equals to 3, and here X2 greater than or equals to 3, here X2 greater than or equals to 1. So these are the rules. So decision tree learning is all about learning the rules in each node. How to decide my node in the first place. See, if you see, can you think of a possibility where I can use X2 as my root node and X1 in my subnodes? Is it possible in this case where I will try to use X2 in my root node and then I'll do my further separation using X1? Is that possible for this kind of data distribution? Yes. How? Maybe something like this. Okay, maybe we'll go back to the original distribution and try. Tell me the possibility where X2 is used first in the root node, and then I want to divide my data points further using X1. X2 first in the root node. Can you tell me how to come up with the rules in such cases? How? Maybe something like this. Something like this. Then after that, within this is here, and within this how? It is not possible, no? One more rule is not sufficient to do the classification. Any other? Any other possibility where X2 is a root node and then X1 in the subnodes? Is it difficult? Is it difficult to use X2 in the root node and X1 in the subnodes? Okay, maybe it is difficult, okay, because in x1 case we were easily doing the separation when I have used x1 in the root node and x2 in the sub nodes. But when it comes to using x2 in the root node, then I have got this possibility. Then I have to come up with two more rules to do this kind of classification. It means that which feature to use in your root node, that is the first question we need to ask, given some data points. See, in this case you are able to visualize the data points, so you are able to come up with some rules, right, on which feature we have to apply the rule. So but when you have a higher dimension, like data set with a very big dimension, so how to come up with the rule, like the first question we need to ask is which feature to consider first in my root node. Okay, so now like in the decision tree you have to first decide the node, and in this node what feature to use. Okay, and on that feature what kind of rule should I apply. Okay, so now can you go back and think, in your linear regression or in your PCA we have actually talked about extracting some important features, no? When you are doing classification, when you have like 3 or 4 features with you, one feature out of your 4 features will be more important, right? Some cases it may happen that like 2-3 features are more important compared to other feature, right? So the importance of features we have seen in your regression case, or even in your PCA, right? When you are doing the dimensionality reduction, when you have some data points with a bigger dimension, you will project it and you will try to extract the important feature. In this case also, if like if you want to construct a decision tree to classify a particular data set given to you, first step is to identify which feature to use in my root node. Okay, so the most important feature will go in your root node. Okay, so and after that, like once you identify the feature, you have to come up with the rule to apply on the feature. So that is all about learning your decision tree. If you come up with a very good methodology to identify the important feature and come up with a rule, then that's about learning your decision tree. Okay, so once after you are done with your root node construction, then you have to go to your sub nodes, and at this particular location also, at the second level tree also, you have to decide what is the next important feature. What is the next important feature in this subset, in this branch, and what is the next important feature. Okay, so we'll stop it here and we'll see how to learn decision tree in the next class. This is what we have done till now. Just a minute, I'll just show you the QR.